So far, I've described how you got all your hydrogen. What about all your other atoms? Where'd you get those? Well, you can thank your lucky stars and the person who first described how you got them, oil. And so, for the first half billion to billion years, as I say, it was too hot. But then after the 380,000 years, you got all your hydrogen. And for the next half billion to a billion years, get more and more hydrogen, and it got hotter and hotter at the center of the universe, and more dense, much denser. So the force of gravity overcame the electromagnetic force and forced everything together, forced the protons and the hydrogen atoms together. They touched and they fused together, and they formed helium with two protons, two neutrons, and two electrons. But also, it produced a heck of a lot of energy. Like you get an fusion hydrogen bomb, and that forced everything apart. So it counteracted the force of gravity, which is trying to attract everything. So you have a tug of war between the force of gravity and the force and a fusion, cosmic fusion, and also a lot of energy be given off. Oh, what do you got? Judy Garland. A Star is Born. Now, if you're Canadian, you might say Mary Pickford, because she was the first female star in Hollywood, called a Sweetheart of America, probably the best known woman in America. Except, of course, she was a Canadian. What's the nearest star to you? Do you know its name? You should know its name. You probably do. It's called the sun. So the sun is a star converting hydrogen into helium and giving off a lot of energy in the form of heat and light. Now a star which is 8 times or more bigger or more massive than our sun, when it uses up all the hydrogen, fuses it all into helium, then it fuses the helium into the next or the other elements in the periodic table until it gets up to iron. Iron's a fairly heavy element, and I forget how many protons and neutrons it has, but quite a few. It doesn't give off energy, no, it requires extra energy. So there's no force now keeping the force of gravity at bay, and the star implodes or collapses almost instantaneously, with such force that it blows up into a supernova. And that gives off so much energy, then you can fuse together the elements of the atoms of iron and most of the other atoms or elements in the periodic table, heavier elements in the periodic table. But it leaves behind a core with all that space missing from the atoms. It's so heavy that 1 teaspoon would be more massive than all the cars in North America combined. Now, I've been talking hypothesis here, so to see if that's true, I tried to take it back into the lab and do an experiment. But when I took a teaspoon, it went right through my hand, because the force of gravity was greater than the electromagnetic force that's keeping everything from touching my hand. It fell right to the center of the earth. And I gave up finding the mass of the cars after 2 or 3. So a star which is over 100 times more massive than our sun, when it collapses into a supernova, it leaves behind a black hole, even more massive than a neutron star. That's what's left behind. Otherwise. Now, a black hole is so massive that even a photon of light cannot escape. When you're on Earth, and you throw a baseball into space, and if you throw it faster than 25,000 miles an hour, it won't come back. It's called the escape velocity of Earth. Try to throw the baseball in a black hole, well, it won't come out because nothing can go faster than the speed of light. You can't come out either. Once you're in a black hole, you're there for keeps. Stay out of a black hole. Even when you get close. Force of gravity on your head would be so much stronger than the force of gravity on your feet. So you'd be stretched out like a piece of spaghetti. Stay away from black holes. Not good for your health. Now what happens to all that material then, the atoms that are created in the star and the rest of the atoms, or most of them, in the supernova? Well, it's all spewed out into space, and gravity takes over again and forms a second generation star. Our star is a third or fourth generation, created some 4.6 billion years ago. Now 10 years ago, all the scientists were saying, Big Bang started 13.7 billion years ago, and the solar system and the sun was formed 4.5 billion years ago. So, did they find another piece of evidence, or come up with another theory? So here's a case where then they had to modify their scientific fact to incorporate any new evidence that they had. So once again, follow the science, but again, a piece of evidence came up that you have to modify that so-called true scientific fact to something perhaps that is at least closer to the truth, if not the ultimate truth. So your atoms, went through an astronomical number of events. You could have one carbon atom in one finger that's created in one star of a star of up to 2 billion or 200 billion stars of over 200 billion galaxies. And another carbon atom in another finger, or the same finger, from another star of up to 200 billion stars, and up to another over 200 billion galaxies. So just think of the number of events that went through for you to be here. And how old you are. Well, most of you is 13 billion. 13.8 billion minus 380,000 years. Your hydrogen, but the rest of you is created between 13 billion and 4.6 billion years ago. Somewhat was 8.5 billion years ago. So, an astronomical amount of events, literally and figuratively. So that's basically how you got what you're made of, and how you got all your basic building blocks, even though science does not know some of the most fundamental questions about that. But where are you? Well, I guess if you're taller, you occupy more space than if you're shorter. Eisner, which is over 2 meters tall, he's one of the fastest servers in tennis. He has more leverage. And Ronick is another fast server. He's 6'5". So there's some advantages of occupying more space or being taller. But if you want to appear to be somewhat more average, then you have to measure yourself in larger units of measurement. So instead of saying you're 2 meters tall, you could say you're 2/1000ths of a kilometer. Or use the distance to the moon, some 384,000 kilometers. So he's just a fraction of that. Or the distance to the sun, some 93 million kilometers away. Or Pluto, 7.5 billion kilometers away. Or the nearest star, Proxima Centauri, 40,000 billion kilometers away. But when we get to that number, large figures, we use a different measurement. The measurement that time takes to go to a certain object. For instance, it takes 1.2 seconds for light to come from the moon to you. Now, when Armstrong was on the moon, and Houston asked him, "How's it going?" And Armstrong said, "Well, pretty good. Very, very good, thank you very much." It took 1.2 or 3 seconds for the radio waves to reach the moon, and another 1.2 or 1.3 seconds for the answer to come back. So there was a delay of up to 3 seconds. And radio waves are part of the electromagnetic spectrum, so it's the same for light. When you look at the sun, you don't see it as it is now. You see it as it was about 8 minutes ago. So the distance you say there is 8 light minutes away. You look at the Pluto, the light comes from that, takes 4.6 hours. So Pluto is 4.6 light hours away. The nearest star, Proxima Centauri, is about 4 light years away. Andromeda, the nearest large galaxy, is 2.5 million light years away. And looking through the Hubble telescope, you can see a star with light takes 13 billion years to reach us. So it is 13 billion light years away. So when you're in that room when you finally get to meet somebody, you ask them, how's it going? And you want to know how it's going at that time. But you'll never know. Because you don't know how he is now, only how he was billions and billions and billions of Planck times ago, when the light left him to reach you. And you'll never know when you look at the moon. You don't see it as it is now, but as it was. 1.2 seconds ago. So basically you're looking into the past. Do you believe in ghosts? Well, maybe you should. Because if you go outside and look at a star, it could have already died. But the light is still coming from the star to reach you. So basically you're looking at the ghost of the star. You never see anything as it is now, but as it was when the light left it to reach you. Now, if you're short and you want to appear to be taller, being short has its advantages. Gymnasts are usually shorter, and of course jockeys. But if you want to appear to be more average, quote normal, then measure yourself in smaller units of measurement. Instead of saying you're 1 meter tall, you could say you're 100 centimeters tall. Or you're 1,000 millimeters tall, or 1,000,000 micrometers tall. Or you can say that you're 1.6 times 10 to the 35th Planck length. So Planck also said that space or distance is discontinuous. So the shortest unit of distance as well, which is 1.6 times 10 to the minus 35 meters. A Planck time is, and then it's about 5 times 10 to the 44th seconds. And it's the time it takes light to travel 1 Planck length. 1.6 times 10 to the minus 35 meters. So what part of space then do you occupy? Infinitesimal amount of space between 1 Planck time, 1.6 times 10 to the minus 35 meters, and 13 billion light years. So that's where you are. Now we talked about your science can tell you your physical attributes, and you're physically made up of atoms, but you have other physical attributes too, like your weight. Now in that room, maybe you should have been noticed because you're an attractive person. People are attracted to you, and you're attracted to people as well. But you say, no. From a distance, maybe I look somewhat attractive. I'm somewhat attractive. But when I get closer, you'll see that my flaws, I may be grossly overweight, I may even be fat. But you're wrong. The closer you are, and the fatter you are, the more attractive you are. Newton saw an apple fall to the earth back in the 1600s. And he said that the apple was attracted to the earth. He even came up with a law or a formula to describe that attraction. He said it's proportional. It was a proportionality, and you can change your proportionality into an equation by just adding a constant. So let's say it's equal then to the mass of the apple times the mass of the earth divided by the distance between the center of the apple and the center of the earth squared. And what's that? Well, that's gravity. That's the force of gravity. So Newton came up with the formula for the force. But you say it'd be kind of difficult to measure that attraction in that room because you're not really massive enough, nor is your friend or your other person. But because he also said that there's, of course, attraction between any two objects. So the attraction between you and the other person in the room would be equal to your weight, your mass, times the mass of the other person, divided by the distance between you two, and squared. But you're not that massive enough to be noticed yet. Your attraction, so go outside. You're more attractive to a mountain, or you're more attracted to the earth itself. To measure that attraction, there's an instrument you can slide in between you and the earth. And it's equal to your weight. I keep saying weight. Your mass times the mass of the earth divided by the square of the distance between you and the center of the earth. And that instrument is called a scale, and what it measures is your weight. So that's what your weight is. I'm going to stop here. Sorry.